So in this video, I'm going to walk through part of our regression mediation activity with you. So in this activity, we're going to use the same data set that we were using in the moderation activity and in the missing data activity. These are the data from the high school and beyond survey. So there's this hsv2.save file that's available on Canvas. And it's in the, you can find it in the moderation activity. You can download the data set right here. So we're going to start. I'm going to let you answer the first two questions on your own, and I'm going to walk through problem number 3 with you, and then I'm going to let you do problem number 4 on your own, and let me know if you have questions about it. So we're going to start off just conducting a simple mediation analysis where math scores affect science achievement directly as well as indirectly through reading. So math scores are our main variable of interest, and reading scores are our mediator variable. So, in this process, it's expected that math scores will have a positive relationship with science scores when reading scores are held constant. So that's that direct effect of math on science scores. That's just our standard OLS regression where we would enter both math and science, we'd enter both math and reading scores in the model. So we would regress science on math and reading. That would give us in the direct effect of math on science scores controlling for reading scores. We also expect math scores to have a positive effect on reading scores, which will then in turn have a positive effect on science scores. This is our this is our indirect effect of math scores on science scores. We think that math is not only going to have a direct relationship with science achievement, but it's also going to indirectly impact science achievement being mediated through reading. So increased math scores are going to be related to increased reading scores, which will in turn be related to increased science scores. So usually our first step in a path analysis or mediation analysis is to draw a diagram of the mediation process. So let's do that now. So I've started drawing these here. We typically in path analysis use rectangles to represent observed variables, and you'll see circles or ovals used to represent latent constructs, or variables that we don't have a direct measure of. So that's why you'll see in here that I'm going to use all rectangles or squares, because all of our variables are observed. So this is how we would draw our path diagram. So math scores have a direct impact on science scores. Math scores also have a direct impact on reading scores, and reading scores would have a direct impact on science scores. So in this path diagram, D here would represent the direct effect of math on science. A times B here would represent the indirect effect. So the indirect effect of math on science is being mediated through reading. So the indirect effect would be the product of the direct effect of math on reading and the direct effect of reading on science achievement. I've used this diagram here just to represent the total effect. So C here then is the total effect of math on science achievement. And the total effect is just a sum of the direct effect here and the indirect effects. So we could say Well, the total effect equals the direct effect plus the indirect effect. So in our case, our total effect was C, direct effect was D, and then the indirect was A times B. That's how that I have them diagrammed in this model here. So when I say we're going to draw out our path diagram, this is what I mean. We want to visually represent what the how this model should be representative. What is the causal model that we're wanting to apply? We want to say that math scores will have we're directly related to science achievement. We also think math scores would indirectly influence science achievement through reading scores, so that math scores have a direct impact on reading scores, which in turn would have a direct impact on science scores. If we were going to build this as a causal model, we want to say that math scores cause the increases we see in reading scores and science scores. We would want these to be temporarily related in time. The math achievement have to come before reading achievement. So that's a little bit fuzzy in this situation. So I'm just really using this as an example of how we can just estimate path analysis models and estimate the different coefficients from these analyses. I'm not necessarily saying that this is a causal analysis. For us to make causal claims, we'd have to have a strong theoretical background, and we would want our exogenous variables here to come before, and to come chronologically before any of our endogenous variables as well. So let's go back, let's estimate model 1. So to get the total effect, so to get this effect here, C, right, to get the total effect of math achievement on science achievement, we basically just regress our independent variable math. We always regress your dependent variable on your independent variable. So we regress science achievement on math achievement. Notice in this model, we don't include any mediators in the model. Notice none of the mediators are in this path diagram. To get the total effect, we want to know just what is that total relationship between math and science achievement. And then we're going to decompose the total effect of math achievement into a direct effect and into an indirect effect. So let's go to our syntax file. So we need to open our data set. I'm going to copy in my file path. I have it here. So copy in where you have this, your HSV2 file saved. And there we go, we got it opened up. And then now we want to regress science achievement on math score. So we enter science, then in our dependent variable line, and enter our independent variable math on the slash methods enter line here. So we run this equation, and so our coefficient estimate here for math now, this has been our total effect of math on science achievement is 0.667. This is our total effect. This is C in this diagram here. This is our total effect of math on science achievement. Here's our regression equation. It's just 16.758 plus 0.67 plus 667 times math scores. That would be our regression equation here. So this is the total effect then of math scores on science achievement. We'll now go to our second model, Now we can decompose this total effect into two components. Remember, a direct effect and an indirect effect. Remember, our total effect was just the sum of the direct and indirect effect. So the direct effect, remember from our path model here, is D here in this. So it's the impact of math on science achievement, controlling for reading scores. So basically then we're going to regress science on both math and reading here. So let's go to our syntax. And so now we want to compute the direct effect. Our dependent variable is still science. And this time we want to enter both math scores and reading scores in the model. So now we have for math here, this is then the direct effect of math achievement on science achievement. Okay, so 0.402 then is our estimate of our direct effect. So for every 1 unit increase in math scores, we would expect science achievement scores to increase by 0.4 units, controlling for the effect of reading scores. This unstandardized coefficient here for reading scores is this B coefficient here in this diagram. So in this model, we now have our estimate of D and our estimate of B here. Since we also have our total effect here, we can calculate our indirect effect by just subtracting out. Remember, our total effect was, what was it, 0.667. Our direct effect was 0.402. And then our indirect effect is here. We could just subtract 0.402 from 667, 0.667 minus 0.402. And then I get my indirect effect, 0.265. We could also calculate our indirect effect by running this regression model, by regressing reading scores on math achievement and calculating this coefficient here. So that's what I'm asking you to do in model 3. You know, to compute the indirect effect, we can run one more regression model, this time quantifying the effect of our independent variable on our mediator. So let's run this model. This time our dependent variable is reading, and our independent variable is again our math scores. And now we have A in our diagram here. This coefficient estimate is A from our diagram, 0.725. Is right here, 0.725. So another way we can get our indirect effect is by multiplying this coefficient by this coefficient. So it was A was 0.725 and B was 0.365. And again, we get 0.265. 0.725 times 0.365. And I got 0.7264625. So you round that off to 0.065. So round it up and we get the same thing. One issue with calculating our indirect effect either either one of these ways is we don't get the statistical significance of our indirect effect. In Darlington Hayes book, they talk about 3 different ways that you can assess the statistical significance of an indirect effect. One is the Sobel test. It's basically you calculate a standard error by hand for this indirect effect, and then you compare the ratio of the indirect effect to the standard error to a Z distribution, and they give the formula in the book for doing that. Another way is that you can bootstrap the confidence interval, and basically by that, basically a bootstrapping, what it does is it's going to take your data set here of 200 participants. We're going to just randomly sample 200 people out of this data set with replacement. So, that means that individual 2 could be in this next bootstrap sample more than one time. Person number 4 could not be in it at all. So we would randomly sample with replacement 200 cases, whatever the size of your data set is. And you would do that, say, 5, 10,000 times. So then you would have 5, 10,000 data sets, complete data sets, and you would run the path analysis on each one of those data sets, calculating an indirect effect, and then you would take the variation in that indirect effect as an estimate then of the standard error of that indirect effect. So that's what they're talking about with the bootstrap confidence interval. You'll need to implement this in SPSS, you would need to use the process macro, which we'll talk about. And then the third step, the third way you can calculate the statistical significance of the indirect effect is through what are called Monte Carlo confidence intervals. And basically what you're doing here with the Monte Carlo confidence intervals is, instead of creating additional data sets like you're doing in the bootstrapping case, you're sampling from a distribution with a set mean and standard deviation. Basically, we're sampling from a normal distribution with a mean set to the mean is set to the coefficient estimate, and then the variance of the distribution is set to the standard error of that coefficient. And so we're using the rule here that the indirect effect is equal to the product of the direct effect of math on reading, and then the direct effect of reading on science achievement. And so we would sample from a distribution with a mean equal to the regression coefficient here, and a variance equal to the standard error of that distribution, and the same thing here. So we would sample from that distribution, say 5,000 times, and then we would use the range in those about calculate different indirect effects from each one of those distributions, each time we sample from that distribution, and we would use that then to set variation in our indirect effect. So basically we're calculating in each way, in both the bootstrap or the Monte Carlo, we're putting a confidence interval around this indirect effect. And basically if the confidence interval contains 0, then it's not statistically significant. If the confidence interval does not contain 0, then it is statistically significant. So let's go back to our syntax here. And so what I've done right here is I've written some syntax that will compute the Monte Carlo confidence interval for you in SPSS. So if you were doing a path analysis in SPSS, you didn't want to have to use a separate macro or go into another program to compute the indirect effects. This little bit of syntax here will compute the computer confidence interval on your indirect effect. You can set a random number seed here. You can leave this alone, pick whatever random number seed you want. If you don't do this, then you'll get a different answer each time you run this. And so here we would change on each one of these lines. You would include the coefficient estimate here for the mean of this normal distribution, and then you would use the standard error as the variance of the normal distribution. And basically we're just going to create a new data set where we're going to look through and sample out of a normal distribution with a mean of 0.365 and a standard deviation of 0.066. And we're going to do that 5,000 times and then compute then the indirect effect. So we're going to have 5,000 x1s, 5,000 of our, we're going to call x2. You know, we're going to have 5,000 random draws from each one of these distributions. Then I'm going to calculate the indirect effect. And then here I'm going to look for a confidence interval, the 95% confidence interval, by looking at the bounds of the percentiles here. So 2.5% would be less than this, and 2.5% would be greater than that. That would equal our 95% confidence interval. We'll run this. And now we have a 95% confidence interval. This right here is our 95% confidence interval for our indirect effect. Since 0 is not contained in this confidence interval, it means our indirect effect is statistically significant. So the indirect effect, you know, we're 95% confidence that the indirect effect is between 0.164 and 0.367 here. If you don't feel as comfortable messing around with editing this syntax, I've created a macro that you can use for here for this. We just need to enter our file path for the macro. You can download. I have this available on Canvas site. Here's you can download my macro here. There's my file path where I have my macro saved. And you would just call the macro. Here's the name of the macro, Monte Carlo confidence interval, MCCI. You give the coefficient estimate for path A and its standard error, the coefficient estimate for path B and its standard error, and then you can just set a random number seed. Here, you can leave this part out if you want. And oops, I must not have, I didn't run this. There we go. And then here we go. We have our confidence interval again on our indirect effect. Notice it's slightly different from the confidence interval we computed here before. And it's because we use a different random number. So remember, we're taking random draws from these distributions. And so each time we take a random draw, we get a slightly different value. But notice they're still very similar, 0.16, 0.16, 0.37, 0.37. So, you know, they're very similar. If I changed my random number seed here, let's see, I use 1357 this time. If I do that, I should get what we had originally. So So if you use the same random number seed, you'll get the same results each time. So it's just going to give you an estimate of what the statistical significance of the indirect effect. This creates a new data set, and sometimes it'll close out the original data set. Notice I don't have my original data set down here anymore. So I'll need to go back here and open my original data set back again. I didn't do any data cleaning, so I need to change anything else again. But I'll need that to run the process macro. So if you want to use the process macro that they discuss in the textbook, and I will say the syntax that they provide in our textbook is outdated. That was for the process macro version 2, and now they're in process macro version 3. So use the syntax guide here that I provided. Gives you more up-to-date information on using process macro version 3 than what's actually in our textbook. Was using the old version of it. So we're going to call the macro using our insert file command. To call it, the name of the macro is process. You give the dependent variable. You say y equals the dependent variable with the science. X equals our main independent variable of interest. So this would be our exogenous variable, math. M here is our mediator, so which is reading. Model equal 4 refers to that. So the process macro can be used to estimate all kinds of different mediation models. Both it can be used to estimate indirect effects. It can be used to estimate mediation models that have indirect effects in them. If you look in the process macro appendix, it lists a bunch of different, I think I've already have it opened up on here. It lists a bunch of different models, diagram models. So this would be model 1 here is an example of a moderation. The influence of X on Y is being moderated by this variable W, so that's an that's an interaction effect. Here we're doing model equals 4 because this is an example of a path model. The input X is being, the influence of X is being, the indirect effects of X is being moderated through our mediator variable here. You can see that this is very similar to the path model that we diagrammed here. Where'd it go? Here is an example of where we, each one of these models is doing something different. Here we have 2 interaction effects. Variable X is being interacted by 2 different interactions. Here you have an interaction effect that also has an interaction effect. Only thing you really need to keep in mind, you can read more about it in his mediation, moderation, and conditional process analysis book if you're really interested. That we're going to focus on this specific kind of path analysis here. You would look basically for a path analysis that is the model that is similar to the one you're doing. So this would be, a path analysis where X, our X variable, also includes an interaction between X and W, and so you say they can get very complicated very quickly. So we're going to stick to just a simple mediation analysis. And notice this M has a little subscript I, so we can have more than one mediator variable. So for number 4, we would also use smaller 4. Sometimes I think it's easier, instead of trying to figure out which model Hayes is talking about in his process macro, is to work through the problems step by step, like we did in number 3. I think is an easier way of running a path analysis is to run it manually yourself, because then you can really control what's going on instead of relying on a syntax file like this. So this just says give you the total effect, give you some effect sizes. We want a 95% confidence interval. We want to bootstrap 5,000 samples and then set a random number seed. So this is the same thing. This is the same syntax how you could use to get the Sobel test. We just use this normal equals 1 command. And then to get the Monte Carlo confidence intervals, we use this MC command, and we want to calculate 5,000 random draws from these distributions. And we can set a random number seed here too. If we run this analysis, sometimes it'll take it a minute. So you'd want to check to make sure that science is our outcome, math is our main variable of interest, and M is our moderator. Our sample size is 200. And so then you can see he's going to automatically perform each one of the regression models that we did. Here our outcome variable is read. This was that 3rd model we ran. And here was that same direct effect. This was A in our path diagram here, right? Our outcome variable is read, the impact of math on reading. Number was 0.725. I just goes up to a little more decimal places. And you'll see the R squared, the constant, this regression equation is the exact same that we found when we ran it. Here's our outcome variable is science. And then here's then the direct effect of math on science. This is what we have labeled as D in our path diagram here. And then this coefficient for reading then is then the direct effect of reading on science achievement. That's what we have labeled B in this diagram here. Here's our total effect. And so they label them for a total effect here of math on science, 0.666. And then it kind of gives you a summary of each one of the effects. So here's our direct effect, the total effect of math on science achievement and its p-value. The direct effect of math on science achievement, same thing we found. And then the indirect effect that we found. The indirect effect, the bootstrap standard error, and then the bootstrap confidence interval. Here it also gives us a partially standardized indirect effect and a completely standardized indirect effect. So this partially standardized is where we would standardize just the dependent variable science and not standardized. So we basically leave alone then the value of reading. We calculate the indirect effect. It has the same process as taking the value of the indirect effect and dividing it by the standard deviation of our outcome. That's in a partially standardized indirect effect, and a completely standardized indirect effect is where we've standardized by both our outcome and our independent variable. So this would be the effect, this would be if we took the indirect effect and multiplied it by the ratio of the standard deviation of our X variable and the standard deviation of our outcome. Partially standardized indirect effects are probably more interpretable when you have like a categorical mediator variable. And then the completely standardized indirect effects of high value both your mediator variable is continuous. So these are essentially like your standardized regression coefficients again too. You can do the same thing. Here's the Sobel test and then the Monte Carlo confidence intervals. You'll see that the output is very similar for each one of these. See, here's the normal theory test with indirect effects. That's the Sobel test. So there's the effect, there's the standard error, and that's the z-score that they calculate. And then here it is with the Monte Carlo confidence intervals. So there's the Monte Carlo standard error, and there's the Monte Carlo confidence intervals. Remember, these are very similar to the confidence intervals that we found too on our indirect effect. So that's kind of in a nutshell how we would typically run a mediation analysis. We start off by assessing the total effect of our exogenous variable on our dependent variables. What's the total effect of math on science achievement? Then what's the direct effect of math on science achievement, controlling for reading scores? That would then give us this coefficient and this coefficient. Then we regress reading scores on math achievement to get the effect of math achievement on reading scores. Then, these two coefficients multiplied by each other would be the indirect effect. We could also calculate the indirect effect by subtracting the direct effect from the total effect. And then we have 3 different ways of calculating the statistical significance of the indirect effect. Remember, that is the Sobel test, Monte Carlo confidence intervals, or the bootstrapped confidence intervals. And so you can see that's sort of, here's the direct effect of math on science achievement. Sorry, this is the total effect of math on science achievement, the direct effect of math on science achievement, and then calculating 2 ways to calculate the indirect effect. So I'm going to let you all work number 4 by yourself. If you have any questions, let me know. We can, basically I'm just asking you to conduct a mediation analysis where math scores affect science scores directly, as well as indirectly through both reading and writing. We also want to include covariates for gender and SES in the model, and these variables are exogenous throughout the model. So the first thing we would want to do is just write out our regression model. So here, math scores impact science scores directly, as well as indirectly, both through writing and through reading scores. And we're also going to include covariates for gender and SES in the model. So give this a try and follow the steps outlined above, and let me know if you have any problems or issues. A couple things that are different about this model is that we have 2 mediator variables and we have 2 additional control variables here for gender and SES. And so a little hint is when we're calculating both total effects, direct effects, and the mediator effects, we want to include gender and SES in all of those models, since they are exogenous throughout. They'll show up in each one of those models. We're also going to have 2 different sets of indirect effect, right? We're going to have an indirect effect of math on science achievement through reading, and an indirect effect of math on science achievement through writing. And then we're also going to have, we can then calculate a total indirect effect and then a total effect of math on science achievement. So as you work through, if you have any questions, concerns, shoot me an email and I'll be happy to help you out. If anything's confusing, also let me know. I'll be happy to clarify anything. If you I'm also available, we can meet virtually on Zoom as well to discuss any issues. All right, thank you. I look forward to seeing your work.